We are going to balance an ideal rift basin. A rift basin is a product of extensional tectonics. Tectonic extension can lead to breakage of the Earth's lithosphere, producing a basin which can be symmetric or asymmetric. I have chosen a case of asymmetric basin. It is also an idealized diagram. The asymmetric basin will not be exactly like this. That is why the word ideal has been used. This is the basin area which may be filled up by sediments, and if not, then it can be called as a starved basin. Away from the basin, away from this line and in this direction, and away from this line in this direction is the undeformed rock material unaffected by the extensional tectonics. Since the rift basins are products of extension, and if I think this as one pin line and this as the other pin line, it is obvious that these two pin lines were closer to each other before deformation, and only during extension they have gone far away. The reason of calling this basin as asymmetric is that the slope, suppose it is theta 1 and suppose here the slope is theta 2, as per diagram theta 1 is not equal to theta 2, theta 1 is more than theta 2. This is an indication of asymmetry of the basin. For a symmetric basin, theta 1 is equal to theta 2 or they are nearly equal. Out of these two pin lines, any one of them we will consider strictly as pin line and the other one as the loose line. Where the pin line is selected, where the loose line is selected, it is at the transition between the undeformed rock and the deformed material. Here also between the undeformed material and the deformed rock material, and the pin line is perpendicular to the layer within the undeformed rock. So also here. Let us take this one as the static pin line and this one as the loose line. The loose line must be at some place here. When we look at the undeformed rock layer, a near constant thickness of T is obtained, and in my diagram T is 3 centimeter. We now want to find out how much is the total area within this stretched rock. To do that, I can break this entire area into 2 trapezoids and 1 rectangle, or 1 rectangle and 4 triangles, whichever suits me. I am breaking this into 1 rectangle and 4 triangles. The rectangle is A, B, C, D. The area ABCD is given by the length AB multiplied by the length AD. In the diagram, AB is 0.9 centimeter and AD length is 8 centimeter. So, it is 7.2 centimeter square, the total area. I have to find out the area of the 4 triangles. Let us call it triangle small a, this is triangle small b, this is triangle small c, and this is triangle small d. The areas of triangle small a, triangle small b, triangle small c and triangle small d are half multiplied by base into altitude, that is to be summed up. I start from triangle A, it is 1.1 centimeter multiplied by 1.8 plus, let us take triangle B, this is 1.8 multiplied by 1 centimeter plus, this is 3.1 centimeter multiplied by 1.2 plus 3.1 multiplied by 1 centimeter. This is equal to this much, which is equal to, therefore, the total area is given by 7.2 plus 5.3 centimeter square is equal to 12.5 centimeter square. I want to divide this total area by small t. The total area divided by small t is 12.5 divided by 3 is equal to 4.2 centimeter. If this is the pin line which is static and this is basically a loose line, then this loose line before deformation was located here, and we can call it loose line initial LLI. And now we say that this asymmetric basin initially was of this geometry, and that this total area within the blue rectangle by stretching got distributed into 4 triangles and 1 rectangle. In this way, the area balance has been made. There can be 2 ways of calculating the elongation. Suppose this point is K1 and this point is K2, then K2 after deformation came to this position K3. The K1 K3 distance is the L final minus L initial is K1 K2 distance divided by the K1 K2 distance can be called as elongation, and from there one can find out the stretch, quadratic elongation, reciprocal quadratic elongation, percentage elongation and natural strain or fundamental strain or logarithmic strain. But if I look at the problem in a different way, I consider K1 K2 as the initial distance and K1 K4 plus K4 K5 plus K5 K3 as the final length, K1 K4 plus K4 K5 plus K5 K3 as the final length. Then the calculation of elongation as L final minus L initial divided by L initial will differ from the previous calculation. As one obtains E, one can find out the range of other strain parameters. Same thing can be done from the E known here. One can find out the percentage E, S, lambda, lambda inverse and epsilon. What has been shown in terms of an asymmetric basin with straight slopes, suppose the slope is not straight, rather like this, then also it is possible to balance this cross section and also find out the strain parameters. The approach will be, I can draw a line here and draw a line parallel to this red line. Suppose this is not the blue line, here this is the one and it goes like that. Then this is the point approximately where I can think of a pin line, and here I can set the other pin line and then find out this total area. I have already demonstrated how to find out the area of irregular geometry that is to be applied, and suppose this area is A, find out this distance D, A divided by D is equal to S, call it the pin line, call it the loose line final. Now we can set loose line initial based on S, then say that an asymmetric basin was a rectangle, and in this way we balance the section. This rectangle's area is also A. What I talked in terms of an asymmetric basin, think of a much smaller scale. Say this length is around 7 centimeter and we are dealing with pinch and swell structure, and there we do not do the cross section balancing. Suppose we want to find out the strain parameter E, S, percentage E, lambda, lambda dash and epsilon, then we can do the same process. By the way, this portion is the swell and this is another portion of swell, and this is the portion we can call as pinch. Pinch and swell structures are produced due to incomplete breakage of the clast due to tectonic extension. They are not completely separated pieces of Boudins, but during the process of extension the two bulges or swells were created and a pinch has happened. If the extension had continued for a longer time, there would have been a breakage at this point. So, from pinch and swell structures from Boudins one can find out these parameters as well. Which section to study to do this exercise? For Boudins, we need to look at the neck folds or the scar folds, foliations within the rock that comes close to pinch, and within this neck fold region find out the hinge line, find out its trend and then find out a plane which is perpendicular to this hinge line. On that plane, perform the measurements, consider the pin line and the loose line and get the job done. In the examples, I have considered this one as the pin line, this one as the loose line. It is perfectly okay if you consider this as the loose line and consider this as the pin line. In my diagrams, I have chosen the pin lines over here, where the deformation ends and nearly same thickness of the layer can be seen. But if you, instead of taking here, bring the pin line over there, finally you will find that these parameters, whatever comes out, remains the same, and the cross section balancing in case of rift effectively remains the same,